We tend to think of artificial intelligence as this instant, invisible magic, right? You type a prompt, and a split second later, you've got a whole essay, a brand new image, or thousands of lines of code. But that's a mirage. The race to control this seemingly invisible technology is, in reality, a desperate race to build massive, heavy, intensely physical infrastructure. Today, we're going to unpack the global race to build AI data centers and the hidden, physical systems that actually make the magic happen.
There is a profound disconnect right now between what we see and what actually is. We are living in this software illusion. We think of AI as pure code just floating up in the ethereal cloud, something you can scale up in a few clicks. But the physical reality? The cloud lives in giant, sprawling buildings. Every single time a new AI model is trained, or even just queried, it demands concrete. It demands structural steel, gigawatts of electricity, and miles of liquid cooling pipes. Because while you can scale software in seconds, you absolutely cannot download a high-voltage power line, and you cannot instantly generate a building permit.
To really understand why this massive infrastructure boom is happening right now, we just have to look at the sheer scale of power these models demand. Back in 2017, training the foundational transformer model took roughly 4,500 watts. Fast forward to GPT-3 in 2020. Training that single model emitted 588 tons of carbon. Then look at 2024. Training Llama 3.145B swallowed up 25.3 million watts and emitted nearly 9,000 tons of CO2. To put that into perspective, the average person emits about 18 tons of carbon in an entire year. The computing power needed to train these top-tier models is doubling approximately every 5 months, and the electricity required, that's doubling every single year.
So to handle this kind of exponential, off-the-charts growth, the tech industry isn't just building more of the same server farms. They literally can't. They are having to invent an entirely new class of building. Enter the AI data center. This is a purpose-built, incredibly high-density facility. And here's the crucial part. It's designed from the ground up to operate as one single, massive supercomputer. We aren't talking about the standard data centers of the past anymore. These are the heavy factories of the new intelligence age.
The fundamental architecture here is just completely different. Think about a traditional cloud data center. It's built to juggle millions of small, totally independent tasks, running your company's email server, hosting a basic website, streaming a video. If one server crashes, another one just quietly takes over, and you can mostly keep the whole building cool with standard industrial air conditioning. But an AI supercomputer, it wires together hundreds of thousands of specialized chips, GPUs, using a highly precise flat network so they can share data instantly. It essentially forces all of them to act as one giant, unified brain, performing massive math equations all at the exact same time. And because they're packed together so tightly and working so intensely, standard AC just won't cut it. The heat would melt them. They require highly advanced liquid cooling systems plumbed directly through the server racks.
At the absolute core of this whole transformation is the hardware, the specialized AI accelerators. A single AI server rack is packed with thousands of individual chips, all centered around accelerators like those highly coveted GPUs. Now, these chips are engineering marvels. They are unbelievably powerful. But the trade-off is they run insanely hot, and they demand staggering amounts of raw electricity. Keep in mind, every single piece of heavy infrastructure we're talking about today, the acres of land, the millions of gallons of water, the massive grid connections, all of it exists for one singular purpose, to keep these specific chips fed with power and kept from overheating.
And actually building a home for these chips, it is a brutally slow, heavy-duty construction process. First, you have to secure massive tracts of land and fight your way through local permitting. Second, you have to establish connections to high-capacity grid substations. Third, you construct those complex, facility-wide liquid cooling loops just to manage the heat. And only then, finally, can you install the compute clusters and lay down miles and miles of fiber optic cable. None of this happens overnight. We're talking about years of heavy physical labor before a single line of AI code can even be run.
Just consider the sheer physical footprint of these modern sites. Take Microsoft's new Fairwater facility up in Wisconsin, for example. We are looking at 1.2 million square feet, all under a single roof. To build just this one single facility, engineers had to drive over 46 miles of deep foundation piles into the earth. They used over 26 million pounds of structural steel. They laid down 120 miles of medium-voltage underground cable. When we talk about the cloud, this massive fortress of steel and concrete is the actual physical reality.
And building at this kind of unprecedented scale creates a cascading chain reaction of physical bottlenecks. The constraints are like a game of whack-a-mole. They just keep shifting. A couple of years ago, the big shortage was the chips themselves. But okay, say you get the chips. Well, now you realize they run too hot. So suddenly there's a bottleneck for advanced liquid cooling equipment. You build the liquid cooling, and you realize you need a massive amount of power to run it. You go looking for power, and you hit a wall with the local electricity grid, forcing you to wait years in line just for a high-voltage transformer. And as you try to expand, you need more water and more land, which immediately triggers local permitting fights and intense community pushback.
But if you zoom out, the absolute unyielding constraint of all is energy. And the numbers are frankly hard to wrap your head around. 945 terawatt hours. The International Energy Agency projects that by 2030, global data center electricity demand could more than double to hit over 940 terawatt hours in its base case. Just to give you a sense of scale, the total electricity consumption of the 6 leading tech giants is projected to surge from about 118 terawatt hours today to nearly 300 by the end of the decade. That tech sector demand alone is roughly equivalent to 1% of the entire planet's total power consumption.
Naturally, pulling that much power from the grid creates a lot of environmental friction. Recent studies looking at U.S. hyperscale data centers found that their electricity-weighted average carbon intensity was sitting at around 545 grams of CO2 per kilowatt hour. What does that actually mean? Well, it means their carbon footprint is roughly 48% higher than the overall U.S. national grid average. Why? Because right now, despite all the green energy pledges, about 54% of the electricity keeping these AI facilities running is still being generated by fossil fuel sources.
Because these energy requirements are so extreme, we aren't seeing data centers just sprinkled evenly across the map. They are highly concentrated. Over 90% of projected new compute capacity is clustering in North America, Western Europe, and the Asia-Pacific region. And even within those areas, specific hotbeds like Virginia, Oregon, and Ireland are experiencing massive power stress. These AI factories are essentially pushing local power grids right to the brink of vulnerability. It's a localized crisis that is urgently forcing the tech industry to scour the globe for totally new geographies, places that actually have the untapped grid capacity to absorb these giant new energy loads.
This AI arms race is literally redrawing the global power grid. Tech giants are basically being forced to become energy companies. We are seeing them pour billions of dollars into securing carbon-free, always-on baseload power. I mean, they're literally signing deals to restart dormant nuclear power plants like 3 Mile Island. They're trying to build distributed training networks, spreading the compute load across multiple regions so they don't crash a single local grid. They're engineering massive closed-loop water systems so that cooling water is continuously recycled instead of just evaporated away. And now, even governments are stepping in. Creating AI infrastructure is no longer just tech policy, it is rapidly becoming core geopolitical and national security policy.
All of this leaves us with one final, deeply provocative question. We spend so much of our time arguing about the limits of AI software, right? Are the algorithms smart enough? Will they hallucinate? But the ultimate ceiling for artificial intelligence might not be code at all. It might just be our own human capacity to engineer the physical world. The future of AI is absolutely going to be written in software, but its true boundaries will be dictated by copper wire, cooling pipes, poured concrete, and the physical limits of the Earth itself. The digital revolution is, at its core, a physical one.